Okay, I feel a bit of an alien here today because I'm promoting coal as opposed to extending our hydrocarbon reserves using CO2. But I believe that with the abundant supplies of coal we have worldwide, there's an opportunity for clean coal to supplement the energy supplies for the world. And we have to provide a solution for clean coal, and this has been done worldwide, especially in Asia, where countries such as China and Korea are putting in carbon capture schemes to minimize emissions to the atmosphere. And if we look at the fact that China consumes 49% of the world coal production, we see China as leading CCS in Asia. Another thing to remember, coal is a very low-cost source of energy. We traditionally see it as power stations, but in our particular project, we see it as a way of demonstrating coal can produce synthetic fuels on a cost-effective basis. And in round terms, we can produce fuel, that is diesel and equivalent chemical-grade naphtha at 33 cents a litre at the refinery gate. Obviously, to that you have to add costs for taxation and distribution, but so it's a very cost-effective source of energy. And the interesting thing about synthetic fuels, they don't have the contaminants we find in crude oil production of fuels. They don't have the carcinogenics of aromatics. They are lighter fuel, so therefore payloads in airplanes is lighter, which again gives cost efficiency in flights and so on. So we think coal is a superb alternative source of energy. Today, coal is now being used for different products. We have, for example, in the United States, DKRW is developing a coal-based methanol plant and will convert that methanol into gasoline using ExxonMobil technology. In China, Total, in conjunction with its Chinese partner, is developing a project which converts the coal to methanol and then subsequently into olefins, which then is converted into polymers. Here in the UK, we're looking at IGCC, conventional coal gasification for the capture of carbon dioxide at high pressure for EOR applications. In our particular project in Australia, which is a few slides at the end of this presentation, we have to capture carbon dioxide. The coal is gasified at high pressure. It allows itself to be processed in such a way that carbon dioxide is captured at high pressure itself, which is much more cost effective than what has been done here in the UK in terms of long gannet, where you're capturing carbon dioxide post-combustion at low pressure, which is uneconomic. If you look at this simple flow chart, this reflects what can be put together in our particular project in Australia. Now, this project is totally different to what you can achieve here in the UK for a number of reasons, climatic and otherwise. So here we're gasifying the coal, we're capturing the carbon dioxide, we're using Fischer-Tropsch technology for synfuels production. And by the way, this project is in joint venture with CNOC of China. So our Chinese partners and ourselves are developing this CTL project, which I will give details of later. And then the synfuels can then be converted into power, diesel, and methanol. How do we achieve methanol? Well, in this instance, we take the carbon dioxide, which is dehydrated and compressed. We have buffer storage is the plan. It'll either be stored in an aquifer or a depleted hydrocarbon reservoir. But at the same time, what we're intending to do is to build a commercial plant to demonstrate that carbon dioxide, when reacted with hydrogen, will produce methanol, fuel-grade methanol, which can be added to the gasoline pool as a first stage. And as I said a bit earlier, can be converted into gasoline or olefins or some downstream chemical product. Now, interesting enough, in Australia we have regular sunlight, so we don't have the same issues as we have here in the UK or Europe generally. We work in the desert, and so what we have there is the ability, if we wish to increase the production of methanol using the CO2 which we've captured from the coal processing plant, we can electrolyze water which is produced within the plant itself and convert it into hydrogen, oxygen. The hydrogen then is reacted with the CO2 we've captured to increase the production of methanol. So initially we'll have a 100-ton a day plant. The hydrogen source for that is available from the design margin on the base plant. And if we go beyond that, we would then have to use electrolysis of water. In our particular case, we can produce approximately 10,000 tons a day of methanol, which is a step too far at this time. But by building the first plant of 100 ton a day, we'll actually demonstrate the technology of hydrogen CO2 producing methanol. So our scheme is then CO2 sequestration is a buffer storage, and then the ability to take off that CO2 either prior to storage or subsequent to storage to produce synthetic fuels is the way, we believe, the way forward for CCS. In our particular plant design, we've actually built we'll build the facilities for carbon capture, CO2 dehydration, CO2 compression, so it's ready for transportation by pipeline to the storage site. As far as storage sites are concerned, we have two options: an aquifer storage, deep storage, alternatively a depleted hydrocarbon storage. Each have different pluses and minuses, but so we have the choice to determine which is the most economic and secure. I don't think there's any point in discussing subsurface. That's been well covered by previous speakers. And what I think should be reiterated is that the projects underway in Norway, Algeria and Canada demonstrate the ability to store CO2 safely and also to monitor it. And that's the key thing, is the monitoring of the CO2 over the life of the storage system. The other interesting thing is that is biomass. And again, we can gasify biomass, produce a synthetic gas, which is then bled into the main syngas treatment, because you're talking a different order of magnitude in terms of quantities. Our plant, for the design of the coal to liquids, is 30,000 barrels a day, whereas a typical biomass plant would be maximum, say, 1,000 barrels a day of synfuels. So this is the complex you have. And this suits really an Australian scenario. We're in the desert. There's probably 100 inhabitants within the 200 mile radius of our site. So we don't have permitting related issues. And also we have a very positive government support in the project. That is very important. Permitting. And so here we see the different scenarios of producing fuels, carbon dioxide storage, utilization of carbon dioxide, and also power export. And also you see on the top there, we talk about alkaline fuel cells. Well, in Australia, this is specific for our site, there are many remote townships, not like South African townships, but townships where small populations live, and at the moment they pay $200 a barrel for fuel. So here's an alternative way of delivering DC power to the actual townships and then convert it to AC for domestic and industrial usage. A little bit about our project. We're here. We're very close in Australian terms to Olympic Dam, which is going to be the largest copper mine in the world. We have from Adelaide, which is the nearest major urban development, a railroad and a road that goes right the way to the north to Darwin, and it's close about 50 kilometres to our site. This is our site. This year actually it's been very interesting. We've had a lot of rain, so it's been quite green, but normally it's just a barren desert with just cattle ranchers. Here's some of the samples of coal we've taken. It's a very good coal for this application, although it has a high moisture content. It's subbituminous, but it has no contaminants which actually impair the process. This is the simple process representation. So we have coal and oxygen, gasified, clean out the coal, gas, remove the carbon dioxide, go into a Fischer-Tropsch plant for conversion of the CO and hydrogen to diesel and naphtha, producing power from the tail gas, and then refining the wax that comes out of the Fischer-Tropsch process into diesel, naphtha and other fuels. This is a layout of the plant, and I think the Hatfield plant would be very similar to that, except it won't have some of the additional units, but it's a fairly typical layout of a gasification plant. And then here's some key statistics of our particular project. We have reserves of just under 8 billion tonnes. JORC compliant, which is an Australian measurement which is bankable for finance, is of 1.3 billion to date. We plan to produce 10 to 15 million tonnes a year of coal. Our mine footprint is quite large in European terms, but in terms of Australia it's very small. Over a 30-year production period, it's only 2 kilometres by 10 kilometres. We produce a lot of water, which has its benefits for the local communities, for farming. We export 10 million barrels a year. We also produce that amount of power. And then this is the interesting part, is the CO2. We have approximately 4 million tonnes of year CO2 in syngas. We capture all of that, bar 7.7 million tonnes. We have a lot of CO2 in the fuel gas, and that is necessary as a diluent, because when you combust hydrogen, the temperatures are so high that the materials of construction of the gas turbines won't survive. So we use CO2 as a diluent. However, we can substitute that with nitrogen, which is available from the air separation unit. So we have that amount of CO2 in the fuel gas. That is what will be emitted from the power plant to the atmosphere. However, subject to economics, we can actually reduce that to around 1.5 million tonnes a year versus 2.7. I halve it when we're producing that amount of liquids and power, which I think will be the lowest CO2 emission project you'll get, generally speaking, in the world. Thank you very much.